Okay, so next we will establish that the measurements of the framings will be depending on the length they have. That will be from initial setting of how that will be working, but as well, so far because we created the structural elements, we can see that the analytical model is already being created. So I'm going to Dynamo, I'm going to open the same setting I did last time. You can also use it from a link if you have the reference of 5 notes pulling up from another file, and with those creative words, create the first and another reference, create a complete structure. That can also help you to ace the way the elements are being pulled. So now coming back to here, I'm just gonna save this file as structure. So should be structure conditions. So I'm gonna go back later here. Gonna get rid of this part that it's the one that it's creating the framings. I mean the cross. We're gonna use it for the moment. In the file, I'm gonna get just the that's right, all the generic 150. So select for instance is in that project. Gonna delete it. So I'm only having the structural floors that I want to use. In the frames. Important in this to be working properly is that the same concrete needs to be applied for reducing concrete element speed. Together. So I'm checking it out that the concrete beam is not having a section defined, so I'm gonna check. They have the same material type. So if we review, this framing is being created within a concrete cast in place array. So we need to ensure that same type of material is if the material is the same in both, what we will achieve is that actually the element is having everything joined up. So to check the fancy. And also your reference. Gonna change the material so it becomes cast in place. So the material is called concrete. Cast in place gray, it's this one. So it's been applied. Both the elements and settings are already set. So now we can go back to our drawing, and what we did was create just the framings by the type they are required. But we can make these changes so we can know how many types we want to have. So for that, we need to go to the family we're using. We're having the settings for the concrete rectangular beam. We have one type that it's 300 by 600, 400 by 800. Can also duplicate it. Make another type that is going to be 200 by 400 millimeters. And the last one that will be 500 by uh, so we have different types. Different types, and you need to be sure that those are being applied properly. Something like this. 100, 600. This one says 0.2 by 0.4. So by having those, what we want to know is if they have different conditions. Let's say we want to work it first with the top part of the equation. So I'm gonna just have the preview. Right? Since the elements are not being connected, they are gonna show just the lines we have created. If it's something selected, this. So we're having something like this, which is the grid on the top. And we want to use it so we can analyze how the elements are going to be placed. So for having this property, the floors were deleted. I'm gonna close it first because I wanted to have some feedback. It's now I'm gonna delete framings since they are being created by the walls. So I'm gonna recreate it, but this time I'm gonna use different sizes depending on the conditions they are holding. As well as the columns, I want to recreate them again, but in this case now, I want to use the conditions they have from the length. So I delete them, then I can open the structure by conditions. What it's gonna do, it's gonna be opening just the walls, the same thing, and the categories of the floors. Scrolling, it's having everything set, properly working. So going back to where we were, this is the lining. That's the type of lines it's gonna be using. Like we can also do some plotting, or we can just use it like that. We need to have the length. Because in this case, we're using length as our indicator to know which is the measurement the framing needs to have. Then we want to know which are the type of families of structural framing it's using. It's called incomplete rectangular beam. So we will call it differently instead of just selecting it. We wanted to analyze and think which type of framing it needs to have. So we're gonna go for the Revit elements. Family by name. The name is called rectangular beam, so I'm gonna edit. You select rename, copy the name exactly the way it is. Now I can write it down. So it's calling it. So to bring the family. From the family, we can have the types. From the types, it's telling me we have these 4 types of different elements. They are not sorted out. We might need to sort it so we can go for the type name. They have family type name. You can also sort. Their case is just doing the sorting of the first value, and if it's using it as a text, you will get values on different spots. Now that it's been sorted, we want to find the same element on the list, so we need to have an index of, and you know the drill, this is just for finding elements within a list. and then get into my fix. So with this, we already have different family types being sorted out the way we require. So next to that, we want to establish the conditions so we can have a pre-set of how they're going to be working. So let's say that we need to establish a limit. The first one is going to be for the ones that are 200 by 400. We can set it up that if it's bigger than 3 meters would be the limit. Then for going 5 meters, then having 8 meters and 12 meters. Let's see, we have values in between. So we're having the 5, we're having the 3, we're having the 7. Actually, you can also go a little depending on which is the possible use of the framing. We can extend that. So next thing we're gonna do, we're gonna have a setting of bigger than equals as well. Good. So if this one is bigger than this one, doing a cross product because we wanted to test all of the issues that it's being set. So it's saying it's asking for 4 values. We will do it the opposite way. It will be spoken there relatively. Fine, it's using both. So in this case, it's gonna be much more easier if we just do flatten, because that way we'll have all values being sorted out. So it's giving me which is the actual value is going to be useful. In this case, it's giving me which one is bigger, but we also need to test it with the smaller one. So if we compare, this one has the values we want to find. We want to find to which particular setting each one of these will work. So we're gonna have here the first index of so it's picking the right value for each one of these selections. It's to be honest. And it's telling me 2, 1, 2, 1, 0, 0, 0 because the number 4 it's actually true for our values. Number 4 it's 2.8, it can go with the 3. 5 can go with 2.5 as well. Actually, it's depending on this list. So 5, it's also 2.8, 6, 2.8, 7, 2.5. So there's no values that can go together. If we pick it like that, now what it needs to happen is we're going to use these indexes, get equivalent index, so that they complete these values. So we have the list, we have the indexes, and it's telling us which family needs to be performed with by which element. Now, having the flatten all the curves, you can use the X orientation to be performed in the structural framings in the selection. And the same process needs to be applied to the other part of the selection. So I'm going to use this one. Down, get the curve, gain the parameters value, use it as a structural framings, and use it with the other part. So we can now run the difference. And it's setting something like this. For the ones that are smaller, they will have different sizes. Surely all of them are no. It's getting bigger. The less different elements. So there's still a problem going around here because the elements are using just the first values that are not actually responding. So we need to do a flatten from the location of these elements. So they can perform properly. Yeah, so now we can see that if the length is smaller, the framings are smaller. When they become bigger, they are having different values. Have the same thing on the other locations. So I'm going to approach this one because our problem of joints is having setting of different elements. So deleting just all framings and recreating them with that logic. Yeah. So we can see that if it's longer, it needs to be bigger, and if it's getting smaller, it's having different constraints. In this case, I'm exaggerating the size as it has it, but with the columns and the other elements, we also set that those values are bigger than the ones we wanted. So let's say we can change that fee at least. Meters, I'll double change the equation. Another way of doing it is since we already have the settings of how much they have been separated from here, instead of doing the flatten, we can change the types so they belong together to the same set of elements. So we can use a count and how much elements we have with the level 2. So instead I have 3, 3, 5, 1, and then use a chunk. Now we can we can get rid of the flat and the flatten will more pretty crack as well. And the same thing will apply on the upper part. Just need to copy as well the length. How we build a flatten, it can also work directly. So let's check something really quickly. We're gonna simplify the function so we can use it on all our settings, and we're not copying this setting of code a lot of times. So for doing that, the only thing we need to be clear about is how it works on a single element. So I'm gonna do a first item because I don't want the hierarchy to be changing the way it works. So it's first item, and it's gonna be running around. It's first item. So you're gonna be using it for first item, the way it works needs to be having a length. So in the length. And with that length, we wanted to get us the index and the stop. So I'm just gonna get the count off. So it's having the length, doing the test, having the measurement, finding the first index, and that's the one we're using. So I'm gonna get this one off and select these nodes so they can become the test. Creating a custom node. This custom node is going to require selecting the value from list. Actually, appropriate slots. Selecting actual value from list. So select from a list the best fit or lower value. And I'm going to add it practically, so we're having some settings. So as you have already noticed, I'm using a lot of custom nodes for practically, so that they can be instead of that. So this match. Just need to be sure that it's working with a single element. I'm gonna go and edit custom nodes. Need to check this. So the first item is in here. I need to go out for that. So copy first item. The proper values I'm using is not the first item, it's a curve. So it's going like that. It's curves. Curves to test. Actually, I can also use the length as well. Then connected to here, and it's gonna be not a flat, and it's to be a double. In this case, it's list of possible values as a double, but this is gonna be a list double. So that if the element is being selected, it will work with that until the first index is true, and it will go with the integer. So it will be selected index. 1 second. Saving it all my definitions. So when I upload the new version of Practically, those values will be there. Going back, we need to have the curve length. And it's putting me the data. So if I'm getting off the first item and I'm using it with the same data, it's already doing it on the same way. So you need a particular value. So if I go with the complete set of values, it's giving me the settings for those to work. The only thing required here will be to have a flatten. So that they are of the same structure that we're looking for of this setting. So when they get the index in place, we don't need them chunk anymore. And those can get from here to here. With burning times, I'm creating it properly. So as you can see, the function got a little smaller than that. And we can substitute those values as well on the door part. So we're using selecting single platform list, having the list flattened within the other elements, and using it for the linked list item index. So our next step is to use the same function with all the other elements. So we already created, and it's creating exactly the same result. Using it with the other elements means that we're having this work through here. Comes the template. It runs. Using the same logic, using the same function for the links. Just checking that we have properly created our file. Let's gonna copy this one as well, so let's see. It comes along. So with the level 3 having 2, we have already the values, but we need to split still for the levels so they can work properly. So for doing that, what I'm gonna do is use get account. Same process, remember we need to have things going on the same page. So it's something like this running. It's you level 2, level 3. Yeah, it's having 7 blocks of things. So we can have a shop. Now it's working with the same logic that the other one. So if we get a element agent, so boom the types, and types can go from here within the curves. Same logic needs to be applied down here. So I'm just gonna go for set index, different count, values getting the element, and collecting for the main line. Now, lot of ways to explain it, but logic is what it will give you the way the framing needs to be placed, and it's now in place on all elements. So next we need to get for the column. Okay, so now we're going to create the columns, but based on the criteria are that the columns that are having the most of the framings inside it to be bigger, and as well as they're going down, you need to get much more bigger as well. So that at the end, when it's getting the foundations, it will have the beers at the size it's thought. And lastly, you can place foundations related to that weight that is being placed to the building. Use our previous structure by conditions. Before running it again, we're gonna save it the name. And this time it's gonna call 04 structure for columns by conditions. So we want that the conditions driven to the elements are gonna tell us what's happening. So I'm gonna get rid of the framing settings. Since we're gonna use only the columns. So remain that. So talking about this, we have here the family selector. We would have this for the columns. The columns structure being placed What is missing here is the point list. So let me see if we get rid of the surfaces. Needs just here. So at this point, I'm gonna run it to see where am I, and then I can continue building up the setting for that. Right, so we have the lines being used right here. It's gonna be line by start point label. That is it. I'm gonna be using the intersection points with the geometry being translated. So the lines are created. Those are the lines we want to have as elements. So I'm just checking that I'm going to use different types of framings that I'm having. That run properly, they have the differences. So going back to the structure, we have those lines. And this time, we're going to use the geometry we're getting from the elements collector. So I'm going to draw the category for structural framing. We want to use that as a reference. What about there? So I need to use the same type of selector, which is doing the grouping of the elements. Sometimes so I'm changing that. So we have the framing. The framing is gonna be using the reference level. So I would change the reference level here. Reference level we pull from all the elements, and the elements get location value. I will set the things on order. We can check just by the list. So it's long. They're running the geometry. We need to draw it for the elements in the ones we draw it. So now it's color. We can see the difference in the colors, but they are not sorted out by level height. So we need to modify that one as well. So before doing this, I'm going to do the same method is list sort index of the individual index. So that the level goes to the elevation and the groups go with internet index. Now the list is the elements and the sorted list is the values they are holding. So if you run, yeah, now they are colored to set. And with that, we already know where they need to be intersecting. They set that each of these ones is going to be one level being displaced. Considering that the first level, it's going to be just the basic, so it's not actually modifying it. So let's call it for B the rest of items. Rest of items. Here was the number of lists we're using. We're having 6 lists. If we go to the lines, we have 6 lists as well. So we need to intersect how those are working. So I'm going to move this one a little down. And on the other side, we have this set of lines. So we're going to pull the get location. So it goes at the end. And then what we want to have is to know which lines with which lines are getting intersected, knowing that with the size they have, it's the most weight each column is gonna hold. So I'm gonna use an intersect. Actually, plus intersect method. So since we have the same type of construction, we're gonna make it just with the first item. If we're making something different, we need to take the possible modifications so that will work. Now it's a construct is usually 580 types of intersection, and what I want to have is the 4 indices of truth. The all indices of truth. It's not telling me how many elements are there inside the lists. So it's telling me with how many elements it's each column colliding. So if I get the index, get the equal index, it will have the first, then the size of the elements, and with that size, how big the column needs to be. So we can give it a type. We'll call it get parameter value by name. Then having the type name, and if we go up, we have here the list of type names. So we could use a index of. We know which type of family it's using, how big is it, how is it getting it. So we're not getting the approximate of how many weight is getting. We're just having to work around the idea of how to build it using the parameters of the settings. So we can use this logic to get the number of how big the column needs to be. Just gonna add a zoom button. This case is giving me these numbers. So we can know which columns have the most big column elements, which one has at the lowest spot. And then since they are going 1, 2, 3, 4, 5, 6 levels, that's the lower one. They are giving this chart of how many elements they need to be. So I'm gonna do it within it's called repeated item. One, two, three, four, five, six. 6 times each one. That goes. So we can hold up. There is some continuous of the element. So I have from going from out. So I have from 0 to number. This is bigger than 1. Move one. Yeah. So those 1 to 6, it's gonna be called 0, 0, 1, 0, 2, 0, 3, 0 to 5. And that being said, we can have a equivalent index, which is the list of the elements. Uh, well, no bits. That with a level 2, level 3 is giving me these results. It's gonna go 4, 4, 4, 4, 82, depending on the number of settings. We can now transform it into a sum value. So going from a level of 3 elements, it says here that the line is having 20 elements. So the last one is at the top. We need to make here a something. So actually not something to reverse. It's at least reverse. No. So the first element is having more elements and the other ones are having less. So it's gonna be the lighter, and the other ones are having much more. Then we can use a flatten. Using the flatten, so we can load all values. We can go for unique items. Shut up. And with this, we can give different weight to the types of columns we're going to be using. So going on the modeling part, we have the structure. If we go for a column structure being placed on level 0, geographical columns will be placed height, level 1, schedule. We have a column that is 300 and 450. We'll change it. That's the only button we have. 300, 400, 600. We can also have another duplicate that is gonna be 900 by 130. Same hashes that we with the trainings. So big column. And with those four types will be good enough just to get all the proper settings of the building. So you can come to the top, the same setting we did here. Yeah. You can use now not the complete bin, but the complete column, going to structure and columns, complete column universal, rename. No, on the bottom, giving us the sizes and the elements to be placed. So the only thing we're missing here is how do we set this properly constrained difference between the 2 and the 36. So we can have value, the first one being the value up to 8. Second one, let's place it when you're going up to 16. The other one we place to 24, and the last one we place to 36. So if you use the same logic, we use the select type value from list, thinking that this one is just the element that is the list of possible elements. So it's gonna give us a select index. For those, we can flatten and then actually if we go for the list reverse, we do the transpose because we want to have the first big values, making values, small values, and going up to the lowest values. With those values being placed, now we can use the list sort. So that all of them have a list index value. You have a hidden index. That's telling me which value from the final list needs to be placed. So probably we'll go to 1, 2, 1, 3. So 1, 1, 0, 1, 0, 1, 0, 0, 1. So we see how the element is really, really small in that case. We can also change the factors. Make it a little bigger. So to 40, this one's 30, 35, 15, and 6. So changing it is changing the config. Which type of family needs to be placed. Now that we have the family to be placed, we can use these settings to get another internet index. This is going to be the index, this is going to be the iron, bronze. And now it's giving me which type of family needs to hold on each level. If we continue using the function that we had before here, that it's the columns, you can connect it at the end. This is going to be the structural column types. And the lines are going to go from this setting. But it's the line setting creation weapons. So we have 120 types with a curve. It runs. And so that when the element is already in place, it's having something like this. We can see how the family is getting smaller as the requirements for volume are getting lower. And in that case, it's responding to the number of elements we're getting. So we're thinking in a way that the framings are telling us where to place the next part of the structure.